and job satisfaction. Is it significant? Is it a direct or negative relationship? Direct. And is it, how strong is that relationship? Moderate, right? And if we were to look at the different relationships in terms of strength, what has the greatest strength in terms of job satisfaction? Remember, our variables are pay, promotion opportunities, followed by pay, followed by working conditions. If we were to look at the intercorrelations amongst the various independent variables, and we had to comment on promotion and working conditions, is there a relationship between that?
Yes.
Promotion and working conditions?
No.
That's now that. So, is there a relationship? Yes?
Yes.
Is the p-value less than 0.05?
No.
Remember, it's 0.05. Is the p-value less than 0.05? No, it's 0.543. So that is greater than 0.05. So there's no significant relationship. Okay? So there's no point in even looking at the 0.311, the strength. There is no relationship, so why should we bother to look at the strength? Okay? If we look at the relationship between pay and working conditions, is that significant? Pay and working conditions, that's that particular one? It is significant. Is it significant at the 1% level? No. Is it significant at the 5% level?
Yes.
Yes. So if you were to report, you won't report in a boredom fashion. You won't go, there is a significant relationship between pay and job satisfaction. There is a significant relationship between promotion and job satisfaction. There is a significant relationship between working conditions and job satisfaction. Boring. You'd say there is a significant relationship between job satisfaction and pay, promotion opportunities, and working conditions respectively. Okay? So just avoid repeating the same thing over and over. Then you might want to comment on the strength of the relationship. You'd say that there is a strong relationship between promotion opportunities and job satisfaction, because that is 0.845. Okay? You might want to comment on other strong relationships. There's no point in commenting on the weak relationship. And there's no point in commenting on the strength of the relationship if it's not significant in the first place. Okay. Is that making sense? Everybody clear question?
Oh, sorry, this is a silly question, but just in terms of a table layout, I don't know if it's just my brain, but I would work better if I go along a column and come, sorry, along a row and come down a column. Is there a standard? Should it be, this is presented down a column and then along a row, as it were. That's how you read those.
Okay, because that's how correlations are presented.
Always.
But always. But also, it's also interpreted column-wise, so you don't have to repeat variables when you interpret it. Okay? So if you go column-wise, it's pay to promotion, right? If you went the other way, pay to promotion next appears pay to promotion in that cell.
It's a blank.
Yeah, it's going to be a blank because it's a copycat of whatever's below. Instead of letting it be hanging in the air, you rather put it on the axes. Let's see how best I can.
Yes.
This is not the way to do it. Let's just draw it. See, right? If we went the way you are saying, here's our dimension, right? Our R and our P, our pay, promotion opportunities, working conditions, job satisfaction, right? And then we've got the same thing here, pay, promotion opportunities, working conditions, job satisfaction. Now anything related to itself is going to be 1. Pay related with pay is going to be 1. Promotion opportunities with promotion opportunities will be 1. Working conditions with working conditions 1. Job satisfaction 1. Job satisfaction 1, because it's perfect relationship. Okay? Professor MacArthur correlated with himself is going to give perfect correlation. 1.
Probably
Okay?
not.
So, because it's perfect, it's a 1 and it's on the diagonal, right? So if you're going to go row-wise and interpret, that R value, I'm only going to put the R values, between pay and promotional opportunities, which is currently 0.712, is sitting on the axis, right? But if you took pay and promotional opportunities, it next appears in the table with pay and promotional opportunities, which means the common cell in the matrix will be there. Now, if you do it that way, it means the bottom end of this matrix is going to be blank, and all the top ends are going to have values. And aesthetically, it doesn't seem right. Therefore, correlations are presented that way. It's just a repeat. Whatever you got at the top is going to be at the bottom. So basically, it's, I think, aesthetically presented this way. I don't think there's any other reasoning, because you're still going to interpret the same way. All right. Are there any questions with the correlation? Now remember there we took one scale, 5-point scale, another scale, 5-point scale. We took two variables on a 1 to 5-point interval scale. What happens when you've got a nominal scale, your basic bottom level of, but you want to do the correlation, right? For example, is there a relationship between two nominal variables like viewing TV ads of a product? Yes, I see the TV ad. No, I don't see the TV ad. Do you buy the product? Yes, I buy the product. No, I do not buy the product. Now here you have a nominal, yes, no, and another nominal. Can you do the correlation that we've just done? No, because that was on an interval scale. Now you need to do the chi-square correlation, because that is your basic correlation that you can do for a nominal scale variable. You apply the decision rule in exactly the same way, the 1% or the 5% level, and you get a p-value. The alternate to the chi-square can be the Fisher exact probability test, right? The statistic comes something like this. It gives you the number of people that said, yes, I buy it, yes, I watch the ad, yes, I buy it, yes, I watch the ad, no, I don't buy it, no, I don't watch the ad, but yes, I buy the product, no, I don't watch the ad, and no, I don't buy the product. So it's giving you a matrix against different aspects. This particular example is using price and make of motor vehicles, okay? So we're correlating on a nominal scale, the price of motor vehicle divided on a nominal scale, the motor vehicle make on a nominal scale. It is giving us a Pearson chi-square value, which is this. It would also not just give us the chi-square value, but it will give us the extent to which it is significant. It applies like we did in the first case, against a p-value of 0.01 or 0.05. In other words, the significance of a 5% or a 1% level. You will interpret this Pearson chi-square value in terms of the p-value. Now, if you look at that p-value, here it is here. Is there a significant relationship between the price and make of motor vehicle at the 1% level of significance? No. Why? Because this 0.0244 is greater than 0.01. So there's no significant relationship between price and make of motor vehicle at the 1% level. However, if we were to interpret it at the 5% level, is there a significant relationship between price and make of motor vehicle? Yes, because 0.01 is less than 0.05. So you're going to apply the same rule. You're first going to give your perception of the hypothesis, your hunch, conjectural statement. I believe there is a significant relationship between the price and make of motor vehicle. You present your table, particularly with your Pearson values, and you'll say table 6 point whatever indicates that there is no significant relationship between level of significance. There is at the 5% level of significance. Okay? If we say there is a significant relationship between price and make of motor vehicle at the 5% level of significance, what are we accepting? Are we accepting our hypothesis? There is a significant relationship? We originally started off by saying we are hypothesizing that there is a significant relationship between price and make. At the 5% level of significance, we say there is a significant relationship. So do we accept or do we reject our hypothesis? We accept the hypothesis. Okay? I'll go again. We originally hypothesized that there is a significant relationship between price and make of motor vehicle. We concluded that it is significant at the 5% level of significance. So are we accepting our hypothesis?
Yes.
All right. Okay, just to give you the flip side of it. Suppose that was the result. We said there is a significant relationship between price and make of motor vehicle. Would we accept that hypothesis with this result or reject it? We reject it because now the significance is 0.6737, which means it's greater than 0.05. So we cannot accept the hypothesis. We reject it. Are there any questions?
Sorry, what would you with the value for the chi-square 7?
Well, your chi-square value is basically giving you the value of the correlation. If you were to calculate it on your own without putting it through a statistical package, this value will become very important in terms of interpretation, because then you have to determine the value in terms of a range of values. But when you are given through a statistical package in terms of where the P is equivalent, you will interpret it in terms of the equivalent P, which makes your life that much more easier. Question?
We looked at factors that affect employee motivation. Let's say in literature we found out there are so many, maybe 20 something. Then you want to test on those factors. Does it mean you have to hypothesize each and every factor, and which inferential statistics package would you use to rank them in according to the influence they have on employee motivation?
Okay. To answer the first point first, yes, you would have to interpret all, but don't create too many tables to interpret it. Do this, put all your variables in one table and interpret it from that. Which one to determine the greatest degree of impact? The best statistic at the moment is semantic structural equation modeling. Your structural equation modeling will tell you exactly what impact any one of those factors have on your dependent variable. So I would go that way if you're asking me a general question on which is the best statistic to use. Okay? But if you're asking, should we present all? Yes, if they all are in your study, I would present all, but I would be very cautious to have a study with so many variables. You've got to limit your study some way. You cannot have 20 variables. Okay? Leading to analysis paralysis very easily if you start off there. Prioritize at the beginning. Okay? You find that when cases like that happen, very often items can be grouped together. And perhaps one needs to look at that. How can like items group together? Okay. Then we looked at tests of correlation. What about tests of differences? We looked at gender, we looked at age, we looked at all different kind of biographical variables. We need to know now, are these people with different genders, different ages, showing differences? Okay? Now, when we have a test with only a nominal variable with only two categories, like gender, then we would use the t-test. We want to know to what extent do these two categories of the dimension differ from each other. Do males and females, for example, show different degrees of levels of job satisfaction? Would men and women show different preference for the introduction of flexi time in the workplace? So one variable is nominal and the other variable is on the interval or ratio scale. The difference that you must know is in correlation, we say there is a significant relationship. But in tests of differences, we don't talk about relationship. We say there is a significant difference. There is a significant difference in the levels of job satisfaction of male and female employees. There is a significant difference in the way male and female employees view pay and job satisfaction. Okay? When you've got only two categories, it's T-test. The interpretation, simple as you've done before. Except that this time when you state the hypothesis, you're saying there is a significant difference between males and females regarding pay, promotion, working conditions, and job satisfaction respectively. You're saying all in one. You're going to present your table. Now you're going to interpret. Take the first one, pay and gender. The p-value is 0.01. Is that a 1/8? Is that significant at the 1% level? No. So you're saying it's not significant at the 1%. Is it significant at the 5%? So there is a significant difference between males and females regarding pay at the 5% level of significance. Likewise, there is a significant difference between males and females regarding promotion opportunities at the 1% level of significance. There is no significant difference between males and females regarding working conditions, either at the 1 or the 5%, because 0.062 is greater than 0.01 and 0.05. Okay? Now when you report the results, don't report line by line. Put like results together. There is a significant difference between males and females regarding promotion opportunities and job satisfaction at the 1% level of significance. Those two are 1%, put it together. Then do the 5% and then say where there's no significant difference. Okay? And then decide, is your hypothesis accepted? Fully accepted? No. Partially accepted? Yes. Okay, why? Because for working conditions, there's no significant difference. ANOVA is exactly the same, except that ANOVA doesn't have only two categories. Analysis of variance has more than two categories, like age, 20 to 29, 30 to 39, 40 to 49, 50 to 59, 60 and over. There's 5 categories. Race, black, white, Indian, colored, 4 categories. So we can't use t-test. As soon as you go more than 2 categories, you're going to be using ANOVA. Okay? You can use ANOVA for 2 categories as well, but your t-test gives you a mean difference and a better impression. So when it's 2 categories on your nominal variable, the test of difference is t-test. When it is more than 2 categories on your nominal variable, your test of difference is analysis of variance. The interpretation is exactly the same. If we see the table that you have in front of you, there are no differences between age categories and pay, promotion and working conditions because all those p-values are greater than 0.05. There is a significant difference amongst the people in the various age categories regarding job satisfaction. Now you know there is a significant difference, and it's ANOVA. ANOVA allows you, it doesn't allow you to know where the difference lies. You've got to then go into the mean analysis where you can do a post-hoc shift test, a Turkey's test, different statistics. It's telling you now there's a significant difference amongst the various age groups regarding job satisfaction. It's only telling you there is a difference. Look at the last bullet. It only tells you there is a difference. You don't know where the difference lies. To know where the difference lies, you can either do a post-hoc Chef's test, a Duncan multiple, a Turkey, a student human fuels test. One of those tests will generate the second part of the table that you have here. From here, you can tell where the significant difference lies, and you can tell that right? Because 3.4 against 5 were the 21 to 30s, 31 to 40 was 3.425, 41 to 50 was 3.405, 51 to 60 was 3.955. The older people in the organization in this context are showing greater levels of job satisfaction. So we said, yes, there's a significant difference. We know now where the significant difference lies. Okay? Are there any questions? So you see now, interpretation of statistics is very easy. Don't come in with this fear that, oh, I've got all those stats, I don't know what to do. It's so easy. There is something that triggers you immediately to an analysis. Okay? And then you can go into deeper analysis. But it is actually one rule applies. Look at your p-value. Apply it in terms of your p-value. Of course, I've given you the easiest scenario so far because we've used one pair of variables at a time. Multiple regression, also on a 1 to 5 point scale, says we're now going to look at all three variables. Remember, so far we've been looking at bivariate relationships, pay and job satisfaction. I've really created a mess, hey? Pay and job satisfaction, promotion and job satisfaction, working conditions and job satisfaction. We took each pair as a bivariate relationship, one pair at a time. Okay? Now we're going to be looking at job satisfaction, pay, promotion opportunities, and working conditions all together. Once you have only one pair, pay and job satisfaction, you use the Pearson correlation we used right at the beginning. But as soon as you have one dependent variable and multiple independent variables, you're looking at multiple regression. You want to know what happens when we have one dependent variable and several independent variables. This is where you're going to look at the regress effect. And the regress effect is giving you the multiple R. The interpretation comes from the R square, right? The R square, which will be given by your calculation as your printout of your statistics generate, you will know the R square value. And this is how we interpret it. For example, if for this example, the R square value is 0.63 and the F value, which you're not going to interpret but have to present, is 25.56 and the p-value is less than 0.05, then we are saying with confidence that these three dimensions account for 63% of the variance in the dependent variable job satisfaction. How we got 63? We took the R square and percentage it times 100 over 1 gives you percentage. Okay? So we say that these three dimensions account for 63% of the variance in job satisfaction. What happened to the other 37%? Okay? The other 37% is due to dimensions or variables that lie outside the jurisdiction of the study. It is telling you that these three items put together only account for 63% of the variance in job satisfaction. Now remember, we left out many variables, we left out training, we left out people who felt that the way they relate to their boss, we left out supervisor-subordinate relations, we left with colleague relationships, we left numerous variables that had the potential to impact on job satisfaction. Combined, they are outside the jurisdiction of our study and they are accounting for the other 37%. Okay? So if we were to look at our study and create results like I did for this one, you've noticed that the three variables are accounting for the highest adjusted R square, 0.960. So the three variables are accounting for 96%. But there's 4% of something else that doesn't lie in the jurisdiction of the study. It's due to something else. You might also say, okay, fine. It accounts for 63% of the variance, but what has the biggest impact? You will then look at, in the same statistical of data analysis, but that is the way in which you apply it. Of course, it's very easy to relate it to other statistics that you may use. A question at the back first, and then I'll come back to you.
If it's all right, is that you do the multiple regression and then you find that
It's too small.
yes, let's say we have about 3 variables and then you combine all the 3 into determining the R that you can put in the graph. And then you determine that about 80% shows that is not accounted for as you put it.
Okay, in other words, only 20% of all of this accounts for that, and 80% is, let's face it, it's a quantitative study. It's come right at the end. It's too late for you to change anything except to put it at limitations at that point in time.
Wouldn't that imply then that you probably chose not the best values?
Well, it's giving you a sense, remember in your mean analysis of what went wrong, where you did the deeper percentage analysis, but certainly it's telling you in the end that you got the wrong combination of variables here. Okay? And the only thing you can do at that point is put it under your limitations. And that's the honest truth. That's why conceptualization is absolutely imperative. Ravanya?